Hello everyone. So today we will talk about allylic bromination. Okay. So our today's topic is allylic halogenation. So what is basically allylic halogenation? Let's say I have an alkene like that, CH double bond CH CH2R 2, right? So the carbon which is the sp3 carbon which is adjacent to the alkene. So look at this sp3 carbon. So this is a sp3 carbon, right? So this is a sp3 carbon, and this carbon is basically present in the adjacent position of the this double bond. Okay, so this sp3 carbon is present in the adjacent of this double bond, right? So this carbon is called allylic carbon. Okay, allylic position or allylic carbon, right? Is a position allylic carbon. Now our target is we have to substitute one hydrogen of this carbon by a halogen. Mainly we will substitute by bromine and chlorine. Okay, so how we will do that? We will mainly do these kinds of substitution by mainly three type of reagent. One is called NBS, which we will study rigorously. Then there is Br2, high temperature. Say approximately this temperature should be greater than 400 degrees centigrade, and we also can do the substitution reaction, allylic substitution by chlorination above 400 degrees centigrade. Okay, so with these three reagent we can do the allylic substitution. So that means this will not substitute the alkene, so rather than it will substitute the allylic position. Okay, let's check how it will do the allylic substitution. Okay, so if I just go through the one example, let's say I have a okay, so let's say I have a alkene like that, and in this reaction, if I add Br2 CCl4 and in the same alkene, if I add Br2 400 degrees centigrade temperature, right? What should be my product? So look at here. Here no high temperature is present, so that's why this is a simple Br2 CCl4 bromine addition, and it will attack on this. It will add to this alkene double bond, and it will give a 1,2 dibromo product, right? So this will be the product for the first reaction, right? But here the reaction condition is Br2 CCl4, and this is in 400 degrees centigrade temperature. So that means this will not attack now this double bond, rather than it will attack the allylic position. Now look at this. This is a double bond, and adjacent to the double bond this is a sp3 carbon. So that means this is the allylic position. No? Okay. So that means there should be a substitution in the allylic position, right? So that means here. So this is called allylic bromination. Okay, allylic bromination, rather than substitution, rather than addition with a alkene, it will go for the allylic position if we use greater than 400 degrees centigrade temperature. Now let's look at the mechanism how it will do these kinds of allylic bromination, right? So okay, let's see the mechanism. Okay, so mechanism. Okay, mechanism, right? So what happens in case of if any reaction contains high temperature, heat, and any kinds of UV radiation? So that means this UV, heat, and this all things. Okay, high temperature, heat, UV radiation. Okay, peroxide. Always if these three reagents, these three are present in the reaction condition, most probably reaction will go through through free radical. Okay, so in case of any organic reaction, if you found this UV, peroxide and heat, any of the one among the three, then you have to think most probably the reaction should go to a pathway which is a free radical pathway, right? So that means my reaction should go through a free radical pathway, right? Now here what we are doing in this reaction, we are basically what we are doing in this reaction, Br2 plus 400 degree centigrade temperature, right? So our product is like that. So this is our product, right? So what we are doing, our at first step, what happens, Br2, when we are giving 400 degree centigrade heat, there is a homolytic fission in these two Br bonds, right? So this Br is nothing like that. Okay, so this is equivalent to this. Now if you do the homolytic fission, what happens? So if you just do the homolytic fission, what happens? It will generate 2 Br dot, right? Now this reaction goes to a free radical pathway. Now what happens? Look at the position. So here, this is a sp3 carbon, right? So that means there is a 3 hydrogen. I am writing only one of them because this is important. So this Br, next step in this Br will attack on this hydrogen and this will generate another free radical, right? So that means, okay, sorry, so it will generate, okay, so what will happen, it will generate a free radical like that, and here we will get HBr. Now look at this free radical, right? This free radical is resonating, this free radical can perform the resonance with the double bond and it can stabilize itself, right? So how it will do the resonance? So it can do this kinds of a resonance, okay, and it can stabilize itself, right? So that, and both the structures are equivalent structure, so that means they are very stable, right? So that means what happens in the last step, what happens, we have produces 2 Br dot, so that means 1 Br dot used in the second step. So let's say this is first step, so this is second step. So I have a this kinds of free radical, and in the first step I have used 1 Br dot, so I have another Br dot, and they will basically bind with each other in a homolytic free radical manner. So they will give this kinds of a product. Okay, so this is allylic coordination, how this reaction is goes. So that means free radical, this reaction goes through free radical pathway. So intermediate is a free radical, right? Free radical. So that means product will be controlled by the stability of the free radical. So product will be controlled by the stability of the free radical, right? So product will be controlled by the stability of the free radical. Now let's go for some examples of these kinds of reactions, okay? Because these kinds of reactions are very much important, and JEE and other competitive exams frequently ask the questions from these kinds of reactions, right? So the next reaction, we will solve some examples. Let's say I have a substrate like that, and if I add here Cl2 400 degree centigrade temperature, what should be my product? So look at this, this is a alkene. So if this 400 degree centigrade temperature is not there, so that means I will get a 1,2 chloro product, right? But here, as 400 degree temperature is there, so that means this chlorine will homolytically break to create F dot, and that means there should be a allylic combination, allylic chlorination, right? So that means this is alkene, and after the alkene there is a sp3 carbon, this, so this one is allylic position, right? This one is allylic position, right? So this one is allylic position, right? So that means my product should be, there would be substitution in this carbon, right? So this is my product, right? So if I take another example, look at the situation. So this is my substrate. If I do the same kinds of reaction, let's say Br2 400 degree centigrade temperature, what should be my product? So look at this again. This is this reaction also contains 400 degree temperature, and if you just observe the substrate, so this is a alkene. So after the alkene there is a sp3 carbon here. So that means this carbon, okay, this carbon is a allylic carbon, right? This is a allylic carbon. So this is a allylic carbon. Okay, so substitution will occur in this carbon, right? So that means my product will be here, right? So my product will be like that. Okay, now if I take another example, let's say I am doing this reaction on toluene, right? So let's say I have a product like that, CH3, and I am doing the same reaction, Br2, 400 degree centigrade temperature. What should be my product? Now if you look at the substrate here, so you have to find the allylic position in this substrate, right? So now in this substrate, if you just observe this part of the benzene ring, right? So this part of the benzene ring. So look at, this is a double bond, right? This is a double bond, and after this double bond there is a sp3 carbon, this CH3, right? So that means this position is allylic position. Okay, so this position is allylic position. So substitution will occur on this position, right? So substitution will occur in this position. Okay, sometimes this position is called benzylic position also. Okay, sometimes this position is also called benzylic position. Okay, and here the free radical will be the, what should be the intermediate for this reaction? The intermediate of this for this reaction will be this. Okay, CH2 dot, right? And these are resonance stabilized because this free radical can resonance with the benzene, right? So this will be our product. Now we already talked about the chlorine allylic bromination by Br2 400 degree temperature. Now let's go for the most popular allylic brominating reagent, that is NBS, right? So the another brominating agent, so this is called NBS. Okay, this reagent is called NBS. Okay, N-bromo succinimide, right? N-bromo succinimide. Okay, so look at the structure of N-bromo succinimide. So the structure of N-bromo succinimide is like that. Okay, so this is the N-bromo succinimide. So this is NBS reagent, right? So how I will get this reagent at first? Okay, so how I will get this reagent? Okay, so what is the structure of succinic acid? So succinic acid is like that. Okay, so this is succinic acid, right? Now from the succinic acid, if I can remove this water by a anhydrating agent, that water absorbing agent, that like by P2O5, right? So what I will get? I will get this kinds of anhydride. This is called succinic anhydride, right? Succinic anhydride, right? So this is called succinic anhydride, right? This is called succinic, and this substrate is called succinic. Now with this succinic anhydride, if I react with ammonia, so that means okay, I will write the ammonia in a fancy manner. So that means this is, sorry, I am writing in a wrong fashion. This should not be CH3. So this is my ammonia. If you look carefully, I have written the NH3 and H2NH, right? So the basic reason is that if you react this succinic anhydride with ammonia, there will be dehydration. Okay, so what I will get from this? Now look at this. You may think that this is a amide, so that means this will be this amine. Naturally, amines are basic, right? So there is a lone pair because they donate lone pair. But here, this is not a basic amine, because the proton which is present here, basically the proton which is present here, that means this proton, this is basically this proton is an acidic proton, right? This proton is an acidic proton. Now the question is, why this proton is an acidic proton? Okay, because if you just write the conjugate, this is an acidic proton, because if you just write the conjugate base of this product, so okay, let me clear this at first, then I will discuss why this is a so we are talking about this substrate, right? So we are talking about this substrate, right? now this proton is an acidic proton, right? Why this proton is an acidic proton? Because if you just look at the proton, let's say I am reacting this with a base, right? So this will attack here. Now the product which I am getting after treating this substrate with base, this is minus, right? And this minus charge can localized with this carbonyl compound, so I will get this kinds of a canonical structure, right? In, and this can also resonate with this double bond. So what I will get this kinds of a structure, right? This kinds of structure, right? So I will get this kinds of structure. So this substrate is a resonance stabilized. So, okay, so that means as the conjugate base is stable, so that means this is a acidic proton, right? Now after treating with base, I will generate this, and after generating this, if I treat this substrate, okay, if I treat the substrate with let's say I have some issues with my mouse, so let's say I am reacting this, so there should be a minus charge on this carbon after reacting it. Now if I treat this substrate with Br2, so what happens? This will attack on the Br and this will come, right? So that means we all know that bromine has a vacant D. Due to this vacant D, bromine can accept electron from any nucleophile, right? So this will generate this, right? So this will generate this, right? So this is how I will get. So this is called, and this is basically derived from succinic acid. And after the succinic acid, I am reacting this with NH3, and then I am reacting with base and adding Br2, right? So I will get N-bromosuccinamide. So there is a Br in this terminal, right? Now if you add this reagent, now you have to understand that why this reagent is used. This is popular, okay? Because this reagent itself, okay, if you just forgot to, so this reaction basically leaves a Br, okay? Now if you just a little bit careful about this reaction, okay, so why this now our discussion is why this is popular, okay? Because in this, with NBS solution, okay, with NBS reagent, there is always little bit impurity, always a little bit impurity of HBr, okay? So always in the NBS solution there is always little bit impurity of HBr, right? Now if HBr is present, so what will happen, okay? So if HBr is present, what will happen? So in the NBS solution, if in the pure NBS solution there is little bit in HBr, so what will happen? Very interesting thing will happen. So there is a lone pair, right? So and HBr is a very good acid, so it will take the proton and this will, okay? Now so that means, look at the situation. So Br and here is a plus charge, right? So nitrogen is containing plus charge, so that means situation is very bad for him. So it will try to remove his initial. So bromine will attack here and this bonds will open. So we are basically again getting this product and we are generating Br2, right? So that means this NBS in the presence of this HBr impurity, it's nothing but the source of slow production. Source of slow production of Br2. So this is nothing but the source of slow production of Br2, right? So that means this NBS is nothing but the source of slow production of Br2, right? So now if you add in the reaction medium, Now if you uh, let's say I have a substrate like that. Okay, I have a substrate like that. If I add NBS here, so what should be my product? Okay, now some people can tell that this NBS will NBS is always used in the for the allylic bromination, but this is not true. NBS is nothing but the source of bromine. Okay, now if only bromine is present in the reaction medium, this is only giving you bromine in the presence of HBr impurity, right? So that means this is nothing but the source of bromine. So if you react this alkene with this bromine, you should have the product 1,2 bromo product. Okay, so if you only react the NBS, if you react only the NBS, you should get the 1,2 bromo product. Okay, nothing more. Okay, nothing more you will get, right? Now if you just simply react this alkene in the presence of NBS, in the presence of UV ray or any peroxide, right? Peroxide. So now in the presence of NBS plus peroxide, in the presence of NBS plus UV ray or peroxide, right? So that means it will generate Br2, and this this UV and peroxide can break this Br2 in a free radical, right? In a free radical manner. So that means the source of free radical is basically this UV and peroxide. This NBS is not the source of peroxide, and if the peroxide will create, then only allylic bromination will occur. So that's why only NBS cannot do the allylic bromination. I have to add UV or hydrogen peroxide with NBS to do the allylic bromination. So for this case, you will get only this product. Okay, only NBS cannot do the allylic bromination. It's a very, very important, crucial concept. You have to understand that only NBS cannot do the allylic bromination. With the for the allylic bromination, I have to give peroxide or UV supply for this reaction, right? I have to supply this reaction. Okay, I think it's clear. Now there is another interesting aspect of this NBS, that if I just simply react this NBS, right? Okay, let's look at the situation. Let's say I have reacted this species. So this is my alkene. If I do NBS in the presence of water, right, H2O, so what should be my product? Okay, so as water is present with NBS, what happens? This reaction will go like that. Okay, so let's look at the mechanism. So if I write the structure of NBS, this is the structure of NBS, right? O, this is P, right? So now this double bond will attack on this bromine and this will comes out. So what I am getting here, I will get a cyclobromonium. Sorry, I think I should write in a bigger manner. Okay. So what I am getting a cyclobromonium ion with a plus charge, and I am getting a stabilized carbon ion. Okay, I am getting a stabilized carbon ion. Okay. Now in the reaction medium, what I have water, right? I have water, right? So this water will attack by its lone pair on this carbon, and this will open. So why this carbon? As the bromine is delta plus, so that means it will always pull the electron from this carbon. So this is also a delta plus carbon. Okay, so it's a nucleophilic carbon. So nucleophilic will, sorry, it's an electrophilic carbon. So nucleophile will attack on this carbon, and this bond will open up. So what I will end up with, I have a Br like that, and I have a water molecule attack on this carbon. There is a plus charge, there will be a deprotonation. So my product will be OH Br, right? So when NBS and Br2 will H2 in the presence of Br2, I will I will react, I will get this kinds of product, right? will be this, right? My product will be this, right? So if I just go through more examples about this reagent, it's a very interesting reagent, and this reaction is very much necessary for multi-step synthesis processes, right? So let's take another example. Let's take an unsymmetrical alkene, right? So this is, and if I just react, let's say I am reacting this with NBS, right? NBS and peroxide. So what is the work of NBS? It will give the Br2, and peroxide will break the Br2 in a free radical manner. So that's why allylic bromination can happen, right? So that means this is a allylic bromination problem, right? So I have to, at first I have to find the allylic positions in the substrate. So look at, so this is the double bond. So that means adjacent position of sp3 adjacent position of alkene, which is sp3 carbon. This is called allylic position. So this is one allylic position, and this is another allylic position, right? So now this bromine addition can also occur on this carbon and this carbon, right? So that means free radical can occur here and also here. Okay, so let's say free radical is occurring, free radical is producing in this situation, right? And there is another allylic position for this substrate. This allylic position is basically this, right? So this, right? So that means these are 1 degree free radical. This is a 1 degree free radical, and there's a 2 degree free radical, right? Now if we just count the number of alpha hydrogens, so this free radical is basically contain 3 alpha hydrogens, right? 3 alpha hydrogens, but here the number of alpha hydrogens is basically 0, right? Basically 0, right? Basically 0. So that means as this is a 2 degree free radical, this is more stable. So that's why major product will be, okay. So the major product will be here, right? So the major product that we will found will be like this, right? So bromine will add in this position, right? Bromine will add in this position, right? So because as this is 2 degree free radical, there is 3 alpha hydrogen, only there is a 1. And if you just a little bit analyze this thing, that this thing can do sorry, there is another free radical you can make from this free radical by resonance, that is so this free radical will be, the double bond will be here, so this bond is not a correct bond, okay, so this, okay, so that's means the free radical will be generated here, right? So another product you can find, the product will be, so this will be the another product, this can be the another product of this reaction, and the another product you can expect, okay. So from this alkene we will get the product. If this free radical gives the product, so you will find a product like that, and if the resonating structure of this alkene will give the product, it will give this product, and if this alkene gives the product, it will get this kinds of product. Now if you do the resonance on this carbon, you will also find another product, so that is here, and if you just analyze the product, what you will find that this is basically, these two structures are basically same, okay. So if you just do the nomenclature 1 2 3 4 5, and just 1 2 3 4 5, okay. So 4 bromo, pen 2 in, So and this is also 4-bromo pentol. Okay, so 3 possible products are there, right? So for this reaction 3 possible products are there, right? So 3 possible products are there, but in between these 3 possible products, the major product that we will found, the major product will be the major product that we will found for this, the major product will be this one. Okay, so major product will be this one, because this periodical is more stable. Okay, this periodical is more stable, right? But if in the exam asks how many periodicals products are possible, 3 products are possible, right? 1, 2 and 3, right? So 3 products are possible, right? Now let's go to another example. This is also an interesting question. For this substrate, NBS UV, so UV ray, so there will be a product. So for this reaction, my question is how many products are possible? How many products are possible, right? How many products are possible? So these kinds of questions are very much common in IIT JEE, so that's why we should go through these kinds of questions, so that we cannot feel any kinds of struggle, any kinds of problem during exam for these kinds of questions. Okay, so how we will solve these kinds of questions? So anyone who is seeing this video, please pause the video and try to solve this problem, and then look at the solution. Okay, so at first our approach will be, as UV is present, so that means this product will be go for the periodical mechanism. So that means we have to find the allylic position, right? So this is the alkene, so and there is this is the allylic position, right? This is a one allylic position, and here is another allylic position. So what is the allylic position? Allylic position is the sp3 carbon which is present adjacent to the double bond, right? So that means this 2 allylic position. So at first we will make this 3 periodical. So periodical can present here, so periodical can also present here, right? So that means if I make a periodical on this position, so I will get this kinds of intermediate, right? So another possible periodical is that, I can make a periodical here, right? So now these 2 can give 2 products, right? Now there is another periodical that is possible by the resonance of this periodical. So that is basically what kinds of periodical we will get after the resonance. So look at this. So this is one periodical, and here will be one periodical, and by the resonance of this I will get another periodical. So that is nothing but, so this will looks like that. Okay, this will looks like as following. So this will, okay, so look at the free radicals. Okay, they all are different free radicals. Okay, so we can generate 4 free radicals, right? So if we can generate 4 free radicals, so that means the 4 products are possible. So the one product from this will be so this will be a one product. If this free radical gives the product, so I will get this is as my product, and if this free radical will gives the product, so I will end up with this kinds of a product. So this will be my product. Okay, now if this bromine will give the product, I will end up with this kinds of a product, right? So that means 4 products are possible, right? So that means my answer is 4, right? So answer is 4, right? It's a very simple question, right? It's a very simple question. Okay. It's a very simple question. Okay. Now let's do another example of bromination, NBS bromination, and this reaction is little bit interesting. So if I react, let's say I am reacting benzene, right? I'm reacting benzene with only NBS, right? Only NBS in the present. So what will happen? So that means you will sometime you will be confused. So what should be my product, right? So you will confused what will be my product. Now you can if you just remember what simply NBS, only NBS. What is the function of NBS? With the there is always a little bit HBr impurity present in the NBS, and that will react with the N-bromosuccinamide, and this will gives you the source of slow Br2. So that means this is nothing but the source of Br2, and you all know that the bromine, the reaction of bromine with benzene is a nucleophilic substitution reaction. So it will just simply do the bromination reaction, right? So it will simply do the bromination reaction. Now if you just want to the proper mechanism of the reaction, it's pretty simple mechanism. What happens in case of this? Let's say I have an NBS, right, like that. Only NBS I am using in this reaction. So this. So what happens? Bromine will attack by this benzene like that, and this will opens up. As this will form a stable intermediate, so there is a highly possibility for this reaction. Okay, so what I ended up with. This carbon is attacked. So there is a bromine which is comes from. So there is a plus. So there's an aromaticity regeneration. So that means cyclic conjugation is returned and bromine is added to the substrate. Okay. So simple bromination. Simple NBS is added to the benzene ring, so that means this is nothing but a simple bromination reaction. Okay, so this will happen with nothing but a simple bromination reaction, right? Okay, now let's do one more very interesting problem, and it's a very nice problem. And these kinds of questions are frequently asked in basically IIT JEE exam and JEE advanced. Okay, so let's say there is a OCH3 group here, and I am giving NBS to this substrate, right? I am NBS. What should be my product? Okay, so if anyone wants to know the product, please pause and at first try, then look at the solution, right? So let's say okay. So let's say I have a NBS like that. Okay, so let's say this is Br. Oh, what's happening here? So okay, so it's a very interesting reaction. So what happens? Let's say this is Br. So that means we all know that bromine is nothing but the source of simple NBS is nothing but the source of bromine, right? So now this is an electron donating group. This will, and this double bond will attack on this bromine, and this bond comes out, right? So that means you are again getting a stable intermediate which can facilitate the reaction in this manner, right? And what we will get? We will get this kinds of intermediate reaction. Okay. So what is the condition of this ring? There is a OCH3 plus. Okay, so there is a Br from NBS. There is a proton. So this proton will return back. This will go back. So aromaticity regain, right? Aromaticity regain, right? So that means my product is very simple. My product is let's say this is OCH3, and my product is like that. So that means in the para position of the second ring there will be a simple bromine addition, right? So you have to be careful that this NBS is nothing but the source of Br2, right? The NBS, only NBS will only generate slow bromine, right? This is nothing but the source of slow bromine generation, right? Okay, so this is a very interesting problem. Okay, let's do a last problem of today's lecture, and I will end up this lecture with a very interesting question. This is also a very interesting question, and this question is basically the NBS reagent is sometimes combined with multiple known reagents, right? So let's say I have this kinds of a substrate. I am using zinc amalgam HCl. So I am getting a product called A, and after the getting the product A, I am using two equivalent of NBS and UV ray. I am getting B, and with this P, I am doing elimination reaction by KOH ethanol, right? ETO, right? So C. So what should be my ABC? Okay. So at first we will try how this reaction goes. Let's say this is zinc amalgam HCl, right? So if you zinc amalgam HCl, what it change is it will just simply change this this thing. It will change this carbon to CH2, right? CH2, right? So it will change this CO to CH2, right? So that means this CO will be converted by to CH2. So that means my product will be only this, right? So this is my A, right? Now two equivalent NBS UV. So NBS and UV, it's clear that it will be allylic combination, right? Now I have to find where the allylic positions are present in my substrate. So look at this position. If I just write the benzene ring in a proper manner, so what I will find that okay, this, right? So look at this. After the double bond, there is a sp3 carbon. So this, and after this double bond, there is a sp3 carbon. This, right? So this is the allylic position. This is the allylic position. So that means as I use two equivalent of NBS, my product should be two positions of this substrate will be brominated. Okay. So this is Br and this is Br, right? Now if you just look at the third step, it's a very interesting reaction. If you look at the third step, so it will elimination reaction. What it will do? Okay, so this is not a good color for teaching. So what it will do? It will alcohol OH. It will absorb HBr, right, from the substrate, right? So it's an elimination reaction. So absorption of HBr and absorption of HBr, right? So if you do the absorption of HBr, okay, so this, so I am in data with naphthalene, right? So this is called naphthalene, right? So this is naphthalene, right? So this is our product C and this is our product B. Okay. Now if you want to know the reaction mechanisms of zinc amalgam HCl and this alcohol KOH, so you can please comment on my comment section, then I will make the video for you all. And thank you for your presence in this lecture. Please if you like the lecture, please share and subscribe with your friends, so that's why they can also learn from this video. Thank you everyone for listening to this lecture.